Start recording. Okay, so if you haven't checked out my my repository yet, now would be a fantastic time to go to Canvas and go to the classroom repository. I have linked there. Let me turn off this. So what we've got here. First off, I am lazy, and I don't, and so I haven't ever. So in the past. Geez, it's almost been a decade, almost decade or so. I've been here. I've never actually made a practice final exam, because I actually like this approach much more. If you go to the link I give you on Canvas for GitHub will lead you to github.com/abrosen/classroom. This is my public repository for the stuff. I have a separate one, which I really need to just kind of rename them so that it's more clear to me, because sometimes I accidentally go to one versus the other. So this is all the stuff that I have. Okay. Curved grades. Yeah. So this is a good idea of should update this now that I remember I have this file that I made. This should give you an idea of like what you need to get, because it's fairly consistent from semester to semester. I explained last lecture how I figure out where the curve lies. But again, I guarantee if you get a 90, that's an A, not an A minus. If you get an 80, that's a B, not a B minus. So for the past many semesters, it has been A minus is in 88 and a half or so. Okay. And generally I just shorthand that to 88, because generally there's nobody in between the 88 and an 88 and a half range, generally speaking. So I look for those breakpoints. And often we have some people that get B pluses because they were almost there, but not quite. Again, the A minuses are, the minuses are basically to say, here's a cutoff point where rounding up really doesn't mean anything, right? And the B pluses for the people who were almost to the round up point. So again, I try to do this as fairly as possible.
Good question. So for a student that's been here every day, like submitted like on time and has gotten decent scores, have you had like any student fail at that point?
No.
There you go. So as long as you guys have been showing up.
Which this is the course group of students who have been showing up.
Behold, I'll see you guys next semester in the next course.
So, but anyway, destruct is my day structures folder. Okay, I have some stuff in my algorithm for 3223 that I've put in here as I was going through. But the day structures folder has stuff for the code from the tech that I've been, not that from the textbook, but from my video lectures where I live code and stuff like that. I've also just added some more PDFs, which I should probably throw into a folder, but I have the study guide for the final here, which, because data structure does not really change as a topic, I don't imagine changing this at any point, because it's fundamentals, and these fundamentals, the language may change, but the topics don't, right? So, sorry.
No, it's okay. Please, I'm the one that's interrupting you.
So you want to basically make sure you know your big O notation, just so when we have analysis questions, you can discuss those big O notations. Like I might ask you, in the past I've asked you to compare and contrast sorting algorithms, or hey, why might we use something when we have a data structure or a algorithm that has a worse big O runtime, why are we using it, right? There's different reasons for that. Some reasons are space, sometimes it's context, sometimes it's for small, it works for smaller sets, right? So other things can matter. For another good one is, why would we use hash table? Example, why would you use for a map, you can use a hash map versus a tree map. Hash maps use that constant time runtime. A tree map has log n runtime. Why would I want to use the slower one? So what's one of the things we give up when we use a hash set? So, or a hash map, either one. Well, yeah, we do, that's one reason. A hash table will use up excessive amounts of space. Any other reasons? There is another reason off the top of my head. And that is that if you're using, yes?
Is the whole pigeonhole principle broken down?
Sorry?
Is the whole
That has to do with our space. The pigeonhole principle thing is our space, so we need a waste space for that. The other reason though is because semblance of order. In tree sets, you can at least you can keep things in a sorted order because trees imply order. In a hash map, there is no. They're just everywhere. Although I'm sure there's clever programming that uses up more space that you can handle. For sorting, we typically go over, the ones I typically go over in the exam are insertion sort, quick sort, and partition, and merge sort. Typically what we do, and you'll see this in a couple questions, is I give you a question along the lines of, hey, here are some numbers 5, 7, 2, 1, 4, 8. You get the idea. I give you an unsorted pile of numbers, and I ask you to do the first iteration of quicksort, and with the partition algorithm. That means that that we need to go through this and do the entire, do the partition algorithm, but only one step. Basically, where we translate it into, we select the pivot. Here's everything less than the pivot, and here's everything greater than the pivot, right? Not here's the entire thing sorted, right? We're looking for the first iteration.
Big recommendation, please read the instructions carefully and take your time to understand it.
So for this one, it's a matter of we would say, okay, I will often say use the first item as the pivot. So 5 would be our pivot. Then we go, if you remember how we do it in place, we go up. So we go up looking for the first item that is bigger, which is 7. And then down looking for the first item that is smaller than our pivot, which is 3, and then we swap them. So we get 5, 3, 7, 8, 4, 1, 2, right? Because we swap them. Then we continue until up and down cross their paths. So up looks for the first thing that's bigger, down looks for the first thing that's smaller. They crossed. So we're done. So we're effectively done. The only thing we have to do is swap the pivot with down. In other words, we swap 5 and 4. So that 5 ends up in the middle. And typically this ends up with a different configuration than if you just simply said pivot and then said 7, okay, let's go through and put the stuff that's bigger on the left and stuff that's smaller on the right. If you do that, you end up with, on the greater than side, 7, 8 rather than 8, 7. So it's one of the tells for that. It's effective, it works. So just be sure to know how to do that. Huffman encoding, I don't know if we
did it on the last exam. The only, I would say, I'm not sure exactly.
I'm just trying to remember if we do it on the final, or if I have it on the final. I try to make it not too big, but not too small. I have to actually send an email to the other professors since it's a common final. So your data structures, lists, no linked lists, array lists. Typically, if we're asking you to do code with a linked list or array lists, or linked list specifically, we are not asking you to manipulate nodes directly, right? You're going to be working externally with a linked list using its properties that make it very useful for splitting your stuff. If you have access to the node class, I will basically say this is an internal method for a node. You have access to the node class. Otherwise, the node is private. And so setting the pointers is what you need to use. Otherwise, trying to manipulate with the pointers from outside, A, you couldn't do that because that's private, and B, you're probably going to make it more difficult than you need to. Stacks and queues can be useful. If you remember that first page of questions, right? I do like to have that page of questions saying, hey, which of these data structures is best? Hopefully the people who played Magic the Gathering appreciated one of the questions on the actual exam. I am an avid Magic player. Trees, definitely on the exam, always on the exam. Nice big chunk of the coding is going to be trees. Heaps, right, know about those. And then hash tables. Very often almost all the time on the exam, and we'll go over practice questions like this, you have a question saying, hey, here's an empty hash table, insert these into the hash table, resolve collisions using this technique. Don't make the hash table, don't rehash the hash table, don't make it bigger. Graphs. We will typically give you a graph in an adjacency matrix or an adjacency list format rather than drawing it for you. So part of that will be, here's the graph in this format, make it yourself, and then do one of these things and Dijkstra's on it. We tell you which point we want to do Dijkstra's from. Okay. Now, these are some of these links are dead at this point, unfortunately. Let's see. So let me see how many of these are dead at this point. I've downloaded plenty of them though, fortunately. Don't save. Yeah. So yeah, that link is dead. That's the issue with this. Some of these, like this one, I've made sure to download and I put them on the GitHub repository. Like this one, yeah. So I've just went ahead and put them on the GitHub repository for us, so you'll be able to find them. Occasionally what I do is things like this, where I'll go to like entrance exams for some graduate schools, because some graduate schools do that entrance exam thing. Now, part of the reason I also don't make my own practice finals is that part of what you should know is what you should know. Okay, so you should be able to look at some of these exams I give you and say, oh, I don't need to know this. We didn't cover this, right? Because data structures and algorithms have this overlap, as does object-oriented programming and the data structures class. At various schools, the lines can blur between classes, right? The breakup of material at our school is different than the breakup of material you might have at other schools. So knowing what you're supposed to know is pretty useful for this. Now, this is a written exam for the University of Tokyo's computer science program. 4 problems. Let's take a look at these problems. So for each positive integer, the p-norm, denoted as this, is a dimensional vector. So this is vector arithmetic, right? And asking you to do proofs. You may use the Cauchy-Schwarz inequality. Those of you who have been doing your math probably recognize that term. And if not, and I recognize it, I don't remember it because I haven't had to use it in like a decade. So that's something to study. This is for a non-deterministic finite automata. This is from computational automata class. So if you can do computational automata, you'll remember this. And for those of you who don't, basically anything that is a non-deterministic finite automata can be turned into a deterministic finite automata, which is a kind of graph representation over here of a regular expression. Regular languages and DFAs are equivalent. There's a reason I teach regular expressions. But the reason I teach it in my freshman class and give you the chance to do it as extra credit here is because otherwise you don't get exposure until you have to deal with this nonsense, which they make arbitrarily hard by using over an alphabet sigma, right? We write L of M, the language for M, is a subset of all possible all possible combinations of this, or permutations of this alphabet.
I don't even remember half of this stuff.
So anyway, problem 3, we're going to skip over for a second. Circuitry is problem 4, because because apparently they do hardware. Or something related to circuitry diagrams. Yeah, sequential circuit. Okay. And this is their practice. This is their admittance exam versus their practice exam. They also had to have practice exams. But let's take a look at this. Problem 3. Consider the problem of sorting an array of integers using the heap sort algorithm. Oh, that's this class. Assume that the heap sort brings the minimum element to the front. Answer the following questions. Heap sort consists of 2 phases. Explain what is to be performed in each phase. So those 2 phases, remember, that is the heapify and the sort. Heap sort, easy to remember those 2. In heapify, we turn a heap sort brings, yeah, brings the minimum element, yeah, an array, yeah, we take our array and turn it into a, well, they want to do it to the minimum, but I'm gonna do maximum, we turn it into a max heap, right? We turn it into a max heap, and then for the sorting process, what we do is that we take the biggest element from we quote unquote remove the biggest element from the max heap and put it in the back, swapping it with the element that it's replacing. So that element that's replacing goes into, which is again the back element in the array. We bring that to the front, reheapify, which takes log n time, and then we continue for the n minus 1th smallest element, then the n minus 2, the n minus 3, and so on and so forth. But basically, the biggest item will go to the back, and the second biggest item will go to the back, third biggest item, right? So considering so here's our array of heap sort, and they're using, parentheses instead of brackets, but whatever, different countries, different notations. Okay, draw the tree structure of the heap just after the first phase, which is after we do the heapify, right? Now, answer the time complexity of each phase when sorting an array of length n. Explain the reason, okay? So heapify. If you do heapify correctly, actually, heapify takes only O of n time. It doesn't take n log n, because what you do is that you basically push down everything the minimum amount of times. You can look it up. I believe I go over it in my videos. This question is more of an algorithm. For this one's more of an algorithms question. And same with 5. But the point being is that you can see some of these questions you would be asked on a graduate exam, right? So you've learned quite a bit. If you're interested in this, I believe I have, if you're interested in the answers for this one, bookmarks. No, I said bookmarks. Really? Ooh, interesting. Bookmarks. We are going to go to my exams. URL should be visible in the recording. utokyo-cs, solutions for the practice exams. He has a solutions.pdf, and you can look up the specific solution for this exam. So pretty cool, because I want to go and get to the more interesting things. So other ones I've got are, let's see. I've got one from Harvard's final exam, although this does seem to be, it has some of the questions I really like and other questions that are nonsense, but I'm going to go through this one. I'm going to plan on going through this one from University of Washington, I think. And then this one, no, that's the same one. But I have a few other ones. Yes?
You guys are pursuing a graduate degree here at Temple or in another school after you guys are done? Okay.
If the economy is terrible or it's hard to get a job, that's maybe your best plan. If you're planning on getting a PhD, do not go to a master's program. Just go directly to the PhD program and make sure it's funded, because they should be essentially paying you to get a PhD. Now, at least for an American citizen.
Mm-hmm. The reason why I'm saying is if you guys are planning on doing this, you're going to see a lot of this come up more often when it comes down to data structures. That's plenty of time to
Okay.
tell you.
So let's see what other one we have. So final, that one. Here we go. So this one we'll start with. This one's more of a theoretical one, and it's definitely got more of the algorithm stuff in here from Uppsala University. Time 8 to 5 hours. Is that really the case for this exam? I doubt it. I mean, a lot of these were not particularly the worst. Yeah, I can't imagine this taking 5 hours. All right. So list the following functions by increasing asymptotic growth rate. In other words, which of these from lowest to greatest for big O time. Not really too necessary here, but you can recognize, oh, this is constant time, this is a polynomial, this is a logarithmic time, n log n. So let's see, constant, then let's look at the logs. Log n, 3 log n, then n log n, then n log n squared, then n to the 34th power, right, because that's n to the 34th. And then even though it's 1.1 to the nth power, that's actually pretty terrible. Once you've got the n in the exponent, that's bad. Just not as bad as it could be. This is definitely math that is more for the algorithms class. Although there is worthwhile mentioning this notation over here because the IST people will not be hitting this. We typically annoy mathematicians when we refer to runtime as big O. Big O technically means the upper bound for runtime. It is saying it's never going to be any worse than this. And for computer science, this is useful because Murphy hates us. He hates our guts, and our law, and his law is divine, essentially. However, we do have other tools. We have big omega, which is what the mathematicians have come up with as the symbol to use for the lower bound, meaning it's never going to get any better than this, right? Insertion sort, big omega, is O of n. It's never going to get better than a linear amount of time.
Yeah, mathematicians are pessimistic if they think it's not going to get any better.
It's never going to get any better. Well, insertion sort, it just can't get any better because it's got to spend O of n time reading each element. Think of it coming in already sorted. You can't, it takes at least linear time to check if it's sorted. All right, next one. And finally, big theta. We often, and computer scientists like me often misuse big O, and when we mean big theta means it's never going to get any better or worse, right? This is both the upper bound and the lower bound. So merge sort, for example, would be big theta n log n, because it's always going to be n log n. Always. So that's just worthwhile there. But in this class, we don't care about that too much, right? This is not the math-heavy class. But I do find it, because I like math, I find it incumbent upon myself to kind of say that to you. All right, this is actually a great exam question that I would put on my own exam over here for a theory question. Consider insertion sort and merge sort. And it's all official looking because it's in capital casing, right? For each algorithm, what would be the worst case asymptotic upper bound for each on the running time if you know that the input, and know additionally that the input is already sorted, the input is reversely sorted, the input is a list containing n copies of the same number. For each case in each sorting algorithm, state your answer and justify it in one sentence. So, if I had this on a separate piece of paper, which I would do, give me a second to. I'm just looking for, well, actually I have VS Code open, so let's see. Yep, so I don't really, let's go ahead and create a new SRC, new thing, because I can just write down in the comments, right, new final review. Okay, so, and we've got there, and now we've got a workspace for us. So, nope, that is me compiling that practice, that exam, looking for anything else. All right, where was I? I was in here. All right, so insertion sort versus merge sort. So we're going to go and look at ins versus merge sorted in 3 cases. Sorted, reverse sorted, and n copies. Okay? So let's go with insertion sort first. Insertion sort, what's the worst case? What is the asymptotic upper bound, the big O, in other words, if we know that it's already sorted? So the way insertion sort works is, right, it checks if we've got something already sorted, right? First item we get for free, because of the way insertion sort works. We create a sorted section of the array, and then we try to push each item down into the sorted section of the array. We see we can't push this one down, so we compare these two, and then we go on to the next. We compare these two. Can't push it down. Go on to the next. Compare these two. So this is now the sorted section of the array. These guys. So, and we keep going through basically seeing that we can't push, for each pair of adjacent items, we can't push anything down. So it takes, for insertion sort, O of n time, because insertion sort, because it takes constant time to grow the sorted portion by by a single item each time. So each step only takes constant time because we don't move any items and we only do one comparison. Okay? For reverse sort, on the other hand, this is actually the worst case scenario for insertion sort. It's actually the thing that insertion sort hates the most because it takes the maximal amount of time to do this. Because if you know if you knew additionally that it was going in, that it was reversed, then you would use an easier algorithm just to reverse it. But for the sake of arguments, if you're using insertion sort to do this, then what you would do is you would create your sorted section. Then you'd have to take 6, compare it to 8, and go, okay, we're going to push that down. Here's our sorted section. Then we have 5. 5 has to compare to 8. Then it has to compare to 6. And then 5 is at the front. And then we have to, and so here's our sorted section now. Then we have to do 3 is compared to 8, then 6, then 5. So it swaps with 8, then 6, then 5. And so what's going on here is that we are doing the maximum number of swaps each step. Okay? So the answer is O of n squared time requires max number of swaps each. Swaps, comps, and swaps each step. And what is that pattern? That is, well, we need to make n minus 1 comparisons, then n minus 2 comparisons. Right? I've been showing you this one since the beginning. I tell you, it keeps coming up. That's O of n squared. Right? And then finally for insertion sort. Insertion sort for n copies, that's effectively the same as it being sorted. Right? If it's just that, right? And as long as our comparison is that we basically that this, I think, actually depends on making sure that the insertion sort is written correctly, which is to say that, hey, if items are equals, don't push them down, right? There's no need to swap them. And that seems like to be, and that's what we typically do. We only check to see is, hey, if this item is less than this item, swap them, right? That's what we typically check. So as long as that's the way that this is being checked, then it's going to be O of n time. So I would say this is the equivalent of being sorted, right? Now for merge sort, this is actually a lot clever. For merge sort, this is actually easier. Because we can say for all of them, it takes O of n log n. Because merge sort doesn't care about the configuration of the array. It will always split it into half and split those into halves and to split those into half until we get units of 1, right? And then we have to take them and recombine those layers. Recombine each layer takes, and recombining each layer takes O of n time. There's log n layers. Doesn't matter what the configuration of the items are, it's going to take that amount of time unless it's doing something clever like using and this is why things like timsort, which is the current algorithm that you use instead of merge sort, exists. It takes advantage of times when you do have things that are sorted, because a lot of data comes in this periodic form, right? Where things are continually going up and down. It's not just random. Okay? So let's see. Let's see. Suppose you have a set of numbers where you over some time period do a constant number of insertions and a linear number of lookups of the maximum. So we add a set number of times and we look up a linear number of lookups of the biggest item. To maintain your set of numbers, you can choose between either a heap or a binary search tree. Okay, assume you're minimizing the average total runtime over the period. For each structure, what is the asymptotic upper bound of the average time of the average case runtime, and which of the two structures are used? So we are basically entering a constant number of insertions. That's a weird way of saying we are adding n numbers, because you have the set of numbers, because I might be interpreting this wrong, but you have to build this, and so you have n numbers to add, okay? And a linear number of lookups. So then we have to do n lookups. I know that's weird that they're using constant and linear, and it sounds like the same thing, but it's kind of not. So to maintain your set of numbers, because how to say, the set might have s numbers in it, but we're choosing n of them, and we're adding n into this. So we're not using all the numbers in the set. That's at least the way I'm interpreting it. This is why as a professor I need to be careful with how I word things. All right, so as for each structure, and this is why I say on your exam, write your assumptions down. For each structure, what is the asymptotic upper bound? So if we're doing this with a tree, it takes n log n time to add everything, and then we're looking up the maximum. The maximum, assuming we're going to go ahead and assume this is a balanced binary search tree. The maximum is going to be, here's the root, here's the left subtree, the right subtree. The maximum is always going to be here, so it's going to take log n time. And if we're doing n lookups, it's going to take n log n to create, and then n log n lookups, okay? For a heap, though, right, if we're doing a max heap, right, then in that case, right, we're looking up what the biggest item in this heap is a bunch of times. Well, that's only going to take if once we've made it, the biggest item will always be at the top if it's a max heap, so we can just always find that in constant time. So if we're doing a linear number of lookups of the maximum, O of n time. And finally, if we are to create that, again, it would basically be, if we take our numbers and instead of inserting, that depends on how we're adding them, right? If we're adding them sequentially, it's going to take n log n. If they just simply say, here's all the numbers, we can take that as an array and heapify it, which takes O of n time. So depends on on the interpretation you mean. But the heap in this case I feel is superior. For each structure, suppose you realize you're actually interested, and this is the average case. Yeah, no, I think those two things are basically the same in this case. So I answered this question, but let me think about the average case. I don't see any reason the average case would be different. And if you're watching this from the future and see a reason, please let me know in the comments.
Hit that like video.
Yeah, yes. All right. So we know hash tables are very common. Okay. So we know hash tables are very common. We have seen that under the assumption of uniform hashing, collision resolution by chaining, and constant time computable hash function deletion, and yeah. We also say this can be done to O of n under one additional assumption. I assume that there's, I'm not sure which one they're talking about, whether it being the fact that that rehashing is so infrequent that we can amortize that cost over multiple adds. And I think also that this hash function is good. That's another one. Because this next one is actually one I'm more interested in. This is definitely one. Normally I skip around in this and just go straight to this one, so I don't typically look at those questions. So suppose you have a hash table and insert some elements. When you expect it, you'd see that the result looks at the picture below. Being a good student, you realize there's a problem. So here's our hash table. And it's problematic. Why is it problematic? So that's the first question. Why is this problematic? Why is this? Now this is hashing with chaining, right? Because you've got buckets here, you have multiple items in one slot. Gesundheit. So why is this a bad one?
There's multiple collisions going on.
Yeah, there's multiple collisions going on, but I mean, that's gonna happen in chaining. That's the entire point of chaining. But what specifically is bad? Yes?
Too many spaces?
There's too many empty spaces, right? We have a lot of empty spaces here. Okay, too many empty spaces, so it's not got a good distribution, right? In fact, what spaces are empty? Let's look at those indexes. Do a bunch of the empty indexes have something in common? A lot of the ones, all the odd ones are empty. Not all the empty ones are odd, but yes, all the odd ones are empty. Always, it's always good to be exact as possible with your intention. Okay, all the odd indexes are empty. Okay, so let's see about this. Give an example of a hash function that could give rise to this behavior. Why we get this? So let's look. Sometimes I find reading these things out loud, even in my head, helps figure these things out. So that's good. 0 has 0 and 30. 2 has 21, 31, and 1. 4 has 2. 6 has 33, 63. 10 has 5. 12 has 26, 6. So we're already seeing something here. What's common about each slot by reading it out? What's common about given slot n, what is common about all the items in that slot? Yeah, they have the same ones place. Okay, so let's see if we can't narrow that down even more specifically, right? All the zeros end with 0. 1 goes to 2. All the things ending in 2 go to 4. All the things ending in 3 go to 6. All the things ending in 5 go to 10. 6 go to 12. Okay, so it's twice the one. So the index seems, so the hash function seems to be something along this line. Or a hash function that would work for this seems to be something like this. H of x is equal to x mod 10, to get the ones place, times 2. Right? So double the ones place. And that would get us like 38 into 16, right? Because we take the 8, double it, we're into 16. Okay. What would be a better hash function? Literally anything else? Well, not anything else, right? Right. If I went h of x is equal to 0, that would not be a better hash function. That would actually be worse.
Why is this hash function so top heavy?
So, but one would be maybe instead doing, so one would be h of x is equal to x mod by the length of the array. So in this case, though, so mod by 20. That would give you values from 0 to 19. It would better distribute that. Personally, I might go mod 19, but that gets into stuff in the algorithms class, why you want to use a prime number there. But that's stuff in the algorithms class. The algorithms class, by the way, uses this textbook, Das Gupta's algorithm. It's pretty much been online since forever.
Oh, look, Internet Archive. Weird.
Internet Archive, but also like this one's just simply labeled Berkeley textbooks. But the final draft of this one has been online forever. It's still worth a copy. It's like they've only had one edition. It's like $50. It's not.
It's not expensive compared to like what you'd probably be spending.
Yeah, this is the textbook. It's good. But this is kind of stuff is covered in the first chapter over here because it goes over a lot of algorithms, this number. The other textbook that's used by other schools, they either use this one or CLRS, which is this textbook over here, which is big and it's quite big actually. Quite big. It's one of those big textbooks. Whereas Dasgupta's algorithms is actually quite small. It is small, and it is thin, and it is easy to carry around in your bag, and it's actually quite good. I love that textbook. And again, it hasn't been updated. It's been out since 2006, hasn't been updated. It's fine. It's perfectly fine. These algorithm textbooks typically use pseudocode rather than any programming language because at this point, at that point, you're not really concerned with it. So, okay, where were we? Right, over here. So, suppose we have the numbers 1 to 100 in a binary search tree and wanted to search for the number 45. Which, possibly multiple of the following sequences of nodes could be the sequence of nodes examined. Okay, so this is a binary search tree. So, which of these are possible ones? So let's see if this works, if this would make sense as a tree. 5, 2, 1, 10. Sorry, I did that wrong. 5, 2, 1, 10. Not really. That doesn't really make sense there, right? You can see because to do 5, we would start at 5, we'd look, go left to go to 2, go left to go to 1, then go right to go to 10. That doesn't make sense because if there was a 10, it would have been added here, right? That wouldn't have cut, because remember, with the binary search tree, balanced or unbalanced, the goal is, if it's balanced, to cut the search space in half. Okay, this one is just basically keep going to the left. That's plausible, so keep going to the right. I swear I went to first grade. I mastered this, left and right. Okay, keep going to the right. Okay, 1, 2, 3, 4, 5, 6, 7, 8, that's possible. That's a linked list with extra steps, but possible. Okay, another issue here, 9, 8, 63, doesn't seem, and then 0, no. Okay, 8, 7, 6, 5, 4, 3, 2, 1, that's where we keep going to the left. That's also good. 50.
Wait, aren't you looking for 45? So
Yeah, but it's looking for 40,
I see.
but it's possible. We have not, okay, it's not all the numbers in between 1 and 100. They're just limited between the range 1 and 100. So by not hitting 45, we're saying, okay, we can't, it's not in this tree. So 50, 25, 26, 27, 40, okay, 44, and then going to 42, that 42 kills it essentially, because if we had a 42, well, actually, hold on, 42, that would be great. Nope, that works too, because each step what we are doing, right, 50, that's plausible because 25 is less than 50, keep going up. So if we were at this point and at 44 and 42 were inserted, where should it go? It has to go to the left of 44. So this is a plausible sequence. Similarly, and because this works, then this one works. Now, this one I actually like as a theory question, even though it's silly. Suppose we insert an element into a binary search tree that does not already contain X. Suppose then we immediately delete X from the tree. Will the new tree be identical to the original? If yes, give the reason in no more than 3 sentences. If no, give a counterexample. Draw pictures if you necessary. I assume they're saying deem necessary. But why is this? This one's good because, drawing pictures is always useful. And again, it's one of those ambiguous questions. If the tree is a self-balancing binary search tree, because of the way self-balancing binary search trees work, if you add an item and the tree becomes unbalanced, then in that case, the tree can restructure itself, in which case, since the tree restructures itself, once you do a removal item of that item, there's no guarantee that, there's quite a good possibility that the tree is completely changed now, okay? On the other hand, let's go ahead and assume that we're just working with the ones we did in class, which are not self-balancing binary search trees, because I didn't go over those, right? If we are dealing with a tree, right, and we want to add something to this tree, where does that item go? it becomes, when we add an item, it's a leaf, right? Adding an item becomes a leaf. Adding an item to a tree, it's gonna look something like this. Okay, it could be bigger, it could be smaller, it could be in between, I don't care. The next thing we do is we've added it, and then we have to completely remove it. We immediately delete it. Okay? What happens? Well, deleting is the easy case for removal, right? If we were deleting the root, we'd be in trouble because then the entire tree structure changes. If we're deleting something with the child, that structure changes. But here we are adding an item and immediately deleting it. No intervening operations, right? So because we have just added a leaf and deleted a leaf, the structure of the tree has not changed. Make sense?
Question?
Yes.
If it was a heap instead of a binary search tree, wouldn't you then have to be a counterset because it would?
Yeah, because it would restructure. The heap would definitely reshape, the structure, you'd have the same physical shape, but the numbers would be swapped around into different places.
It's pretty much just understanding how a tree, like, where, like, for example, how a tree, works,
Mhm.
basically. Again, if it's at the root, obviously, it's going to have to change if it's removed, and if it's out of child, it doesn't have to get removed. So just knowing exactly what a tree does is more than enough to help you get to this problem.
Okay. This one, let's see, how much time do I have?
You still have some time.
Yep. So this one, suppose heap in these two values. Nothing like this is going to be on the exam. It's an interesting one, but the answer is that you can draw an example of this, and that's just simply being clever with the numbers you add, where the two things are not equal. Okay, let's see. Don't save. Let's go and look at this one, University of Washington. I like this one. Okay, download the raw file. Okay. Priority queue. So priority queue, this is heap stuff. I like this one because it resembles a lot of the questions I like to use. So in this course, we've seen many different types of data structures, including the following: list, linked list or array, two-dimensional or higher array, a stack, a queue, a hash table. That's our hash map, right? Different schools refer to it as different things. In Python, we call those dictionaries. Tree, binary search tree, undirected graph, directed acyclic graph. And I may have given you that term if you did the last assignment, okay? And the reason I say the word if is because I am dropping besides the one homework you do not do for the, Josephus problem versus encryption, I drop the one you don't do. Beyond that, I'm also dropping another one. So you get one free homework. So if you've been doing your homework up till now, you can just totally not do the last one. The last one is useful to do though, or fun to do, because it concerns this directed acyclic graph. And again, yeah, it defines it here, but we can that acyclic is what makes it scary. But we know what a graph is. We know what a directed graph is. The nodes have everything has directions. A cycle in a graph is where you can keep looping around at a point. A at the beginning of a word means no. It's one of the prefixes that mean no in English. So acyclic means no cycles. Directed acyclic graphs are directed graphs that basically you cannot loop around. They go from some source to some sink, as we like to call it. Basically, think of water flowing downhill. The water never flows back uphill. Okay, we never get one of these Escher diagrams. All right. So for each of the following applications, indicate which of these structures would be the most suitable and why. If it's a tree or graph, give me information on what the nodes and the edges are. So a map of the Puget Sound highway system is used to display traffic travel times on a web page. The map displays the principal cities, intersections, the major landmarks, the roads that connect them, and travel times between them along those roads. Travel time along the same road may be different in different directions. And what I find funny about this one is because of the way I've changed teaching graphs, the number of students who would instantly recognize this as a graph has changed because now we use social networks as the example for graphs because they map much easier. But this one is this is basically how the classical representation pre-social media of what a graph is. We have nodes that are our cities and the intersections and the major landmarks. How you get between those things are your edges, right? So you have basically, whoops, right? You have location A, you have location B, you have edges to connect them, you have location C, how you get there, right? And the idea here is that these edges tell you that you can go from this point to this point, right? You can get to A to B, but not B to A. If you want to go from B to A, you have to go to C, back to C and then to A, right? Now, travel times along the same road may be different in different directions. Well, the travel time is what's stored in these edges. Chessboard. An 8x8 chess board is used for a game of chess. Each square in the board is empty or contains a chess piece. Which data structure is this? What do we use for this? We've done it in class, 2D array. All right, a computer model showing the dependencies between the steps needed to assemble a B-787 airplane at Boeing's Everett plant.
I'm so glad it's not 37 there. Those suckers.
So, it's a graph, yeah, but more specifically, more specifically, a directed acyclic graph. Yes, so this is a directed acyclic graph. Anytime you're talking about dependencies and you're trying to model that as a data structure, that's what a directed acyclic graph is. Because you can't have any cycles in software dependencies, right? Because then you'd have these infinite kind of paradoxes for loading orders, which is, ugh. All right? So, we're not going to do that. So instead, you have these dependencies that say, hey, you should load this first, and then you can say that the incoming edges say that I need that dependency. That needs to be done first. And then you might have things like this. So, right, this is the dependency for these, and then you need to do both of these before you do this. Although once you do this step, you can do this step before going on to these steps. Right? Dependencies matter. The dependencies help us know which needs to be done first. A list of legal words in a Scrabble game. Well, I mean, it's saying list right there, but they may not be the best case. We want to be able to quickly check whether the words used by the players do, in fact, exist in the list. So this one is what? Yep, that's a set. Specifically, a hash set, right? A hash set would use this, right? Or you can use a hash map and just simply check the keys. But if we were trying to say, hey, does this thing exist versus not exist? Or we're trying to say, hey, have I seen this before? Then you're using a set. That's what a set is useful for. Okay. Inheritance relationships between classes and interfaces in a Java program. So in a Java program, right? So let's think about the way Java works for a second. Java says that basically we can have a class here, a class C, okay? And classes basically can have multiple children, okay? But what's the rule for class? You can only extend what? You can only extend the superclass. How many classes can you extend from in Java? 1. Yep, that's 1. Curiously, in Python, how many classes can you extend from? Python don't care. You can extend from as many as you want. And it's just simply the how do you resolve two functions having the same name kind of issue in different programming. Java resolves that by saying you can't extend more than 1, so it doesn't matter. So now, on the other hand, though, in interface in Java, how many, if I'm some subclass, how many interfaces can I extend? How many interfaces can I implement? I can extend one class, but with interfaces, I can implement multiple interfaces. So I can have multiple interfaces. And this no longer looks like a tree, right? It is a directed acyclic graph at this point because trees are technically directed acyclic graphs, by the way, but at this point, but one of the things about trees is that you have one parent, right? That is the big thing about trees, you have one parent. So anyway, let's see. A history list recording the sites visited, another time where we use the term list, but it may not actually be the best data structure. Visited by the user of a web browser. As new sites are visited, they are added to the list. The list also supports the operation of going back to the web page previously visited before the current page and going forward to the next page visited. So we could so there's a couple different ways we could do this. We could do this as a linked list, right, to implement both the back and forward button, and you're just simply moving your position in the list. You add on to the end and move forward once you are, you move on to the end, move current forward every time you visit a new site. Another way we can do this is that we have the back button being a stack, right? And the forward button also being a stack. So when you go backwards, you pop from the stack and push to the other stack. And when you go forwards, you pop from the forward button, add it to the back button. A good example where something might have multiple answers. Okay. All right. Complete the definition, right? So it gives us a BT node here. So notice that they didn't do generics in this class. I'm partial to doing generics. In the year solution, create and use instances of other standard data structures to implement. Complete the definition of the method below to perform a breadth-first search of a binary tree and print the node value in the orders that reach during the search. So, okay, the key here okay, so let's go ahead and basically say, yeah. We're going to go ahead. So typically when we do these search algorithms or algorithms with trees, we have to deal with recursion. However, this is a breadth-first search of a tree. What does breadth-first search look like? We say basically we visit here, and then we visit all the children, all the root's children. Then we visit all the children of the root's children. So this layer gets done first, then this layer gets done first before we visit anything on the layer. So we go through each separate level in order. You can't do that recursively. It just doesn't work. Breadth-first search is not done recursively, if you remember from your graphs. Because remember, trees are just graphs. Okay? Instead, what do? We use a queue to do that. And remember, queue is spelled Q-U-E-U-E. Okay? So we use a queue to do that. So, all right, quickly being put down, we need a private class. We're going to call it the BT node just like they did. Okay, and we're going to say E, right, just simply so that we have a common thing. We're going to go ahead and okay, undent that. I care about my indentation so much.
I mean, when you teach Python, indentation counts.
Yeah. So we have a BT node E left. Right.
Why exactly? Do they care about how we implement the BFS algorithm?
No, it just cares that we do. Okay, that is the left, right, and BT. An E item right there, and where I'm not even going to wait, for a constructor, I do need to actually make a constructor, BT node E item. Item is equal, sorry, this dot item is equal to item. There we go. Next, public, what are we trying to do? Public void BFS, so we're printing it. Public void BFS. Okay, and that's all we need. We don't need a, oh, it wants a root. So BT node, given a root for this, or our starting point, we're gonna just go through this. So the way we implement this is that we are going to say a queue of items, right? We need to because I'm using generics, I will genericize it. And final exam review, I guess I will say fine. Yep, it's gonna use a generic type. Although I could turn it into static and work from there. It doesn't matter. I'll figure it out as I go on. Okay, Q is equal to new. Yeah. Technically, you should use a deck. Outright. So that's a fun thing, by the way, if you haven't ever seen that before, I forgot. Deck is an interface, and look at this. New deck, E is equal to this. I don't know if you've ever encountered this before. This is Python being awesome, Java being awesome, specifically IntelliJ. You can implement interfaces on the fly without ever actually making a new class for them. That's what this did. That's a bit more than I want. So again, in a production setting, you should use deck instead of queue. So what we'll do over here is a linked list. New linked list. There we go. And so we start at the root. What we're going to do is we're going to say q dot, technically it is offer the root to this. And I guess that would be a queue of, it's a queue of nodes, not a queue of items. So and now it's giving me an error because I've got to, there we go. That's why the diamond interface is so useful. So we're going to offer the root to it. Now on the exam, right, you might forget the term because Java uses offer and poll as opposed to more reasonable terms like NQ and DQ. If you put NQ and DQ on the test, I won't care. It's not what I'm testing. I'm testing the algorithmic stuff. Okay, so, and then we just do this while q dot is empty. While that's false, so while not is empty, while we still have something in the queue, what we're going to do is we are going to say BT node current. What we're going to do is we're going to pop off this node, dequeue it, which is poll, to get the thing at the front. We're going to get the front of the queue. We are going to print it out because we're not gathering them or anything. We're just trying to traverse and we're showing how we handle that. Okay, so we're going to print it out. And then we need to make sure that its children get handled, which means that since the breadth first search, we add it to the queue. So we say q dot offer current dot left and current dot right. That's it, believe it or not. This is all that is. It's a very short program if you know your algorithms, which is you just simply add the first item to the queue to make sure that this fires, right? You have a starting point. And then while you have items to go through, you pull it and add to the left and add to the right. Although there is technically something that goes wrong here, which is that if your left and right child are null, we're adding a bunch of nulls into the list. And then when you do this this is fine, but when you try to do null dot left, you get into an issue. So what we're gonna do, there's two ways to do that, which is that you can say, you can put this into an if statement and say, hey, if you just have a null, skip what you're doing. Another way to handle this is just simply say, is over here, which is if current dot left equals null, is not null, right? Surround it with if statements. If it's not null, and then if right is not null. Make sense? And that makes sure that we don't add any nulls into this. So there we go. That's everything it is. Right. Now, let's see. Here's a good one. Here's an adjacency list representation of a directed graph. No weights assigned to the edges. Draw the picture of this graph that has the adjacency list representation. Okay? So, adjacency list. So we have 4 nodes here. A. Let's go ahead and, because we only have 4 nodes, I'm just going to go ahead and write them out. A, B, C, and D. Right? These, 1 second. Yeah. These are those nodes. Right? You know what? It's going to be easier if I do this on a whiteboard. Okay, only a bit more time. Okay. Okay, so we have A, B, C, and D as our nodes. Let's go ahead. Okay. Great. That's perfect, actually. Draw a picture of the directed graph that has this adjacency list representation. So so the way this works is that this is a linked list. Okay, A has B, C, and D. It's not A goes to B, B goes to C, C goes to D. It is A goes to B, C, and D. Okay, next, B has a directed edge to A. We could also represent it as that. We're not picky, especially since it's unweighted. Next, C goes to B and D. C goes to D, and we can either cross or we don't have to. I like to keep things planar if possible, planar, meaning that the graphs we don't have any crossovers. And then finally, D has nothing it goes to. Great. Another way to represent this is an adjacency matrix. Draw the adjacency matrix for this graph. Let's go ahead and grab that, move over here. Here is our thing. So let's go ahead and draw our adjacency matrix for this. Okay, adjacency matrix B is over here is our source. Here's our destination. Okay, and we just basically will have 0. We can do 0, 1s. We can do true or falses. There's different ways to do this. Here I'm just going to do 0s and 1s. If we have something from a source to a destination, we are going to have a 1 in that place. So A goes to B, C, and D. We put a 0 on A0 because we did not have A in this list. We did not have a self-referential edge, or an edge to itself, I should say. B to A, and then B doesn't go to anything else. C to B, right? This is not symmetrical because, again, these are unweighted, these are directed graphs, so there's no reason that you would have, if A goes to B, there's no reason for B to go to A, unless it's listed. C doesn't go to A, but it goes to B, and D doesn't go anywhere. So that's our adjacency matrix. Okay. This one is the other reason I like this one. So again, I'm telling you flat out right here, Dijkstra's will be on the exam. A question like this will be on the exam. I might give you a graph like this. I also might be a jerk and give you something like this or something like this. Right? Something where we have where it's given to you in that form. So consider the following directed graph. Okay. First off, what I will not do, okay, is do what they did here. Because what they did here is an affront to God and all mankind. Okay? We are going to take this, we are going to paste this, and we are going to fix this affront to the deity of your choice, which is we are going to make these into letters. Okay? Because again, what it is that it's so distracting to have that be, one has a 1 goes to 2 with an edge of 3. No. Okay, that does not make sense. We need to use our numbers here. So we're going to go A, B, C, D, E, and F. I want this. I want my problems to focus on the problem, not the mental load of having to differentiate between numbers in different contexts. Okay, we don't use numbers for names and for distances. It's wrong. So how much time? Yeah, this is plenty of time. 4 minutes is plenty of time. Okay, so what we do here is that we are going to create a table to work on. Okay, our table is going to go over here. I'll zoom out a bit. Okay, and our table is going to be A, B, C. Sorry, we got to put it over here. A, B, C, D, E, and F. We have our, and we have, basically it's going to be 2 columns. We have our predecessor, our distance, D, distance to that node, and our P, which is our predecessor. So pred, dist. Okay. So we're going to look from A to all the other nodes. So our distance so A has a distance to 0, and everything else starts out as infinity because we don't know how much it's going to get to. Okay. We get to A from itself, well, from nobody else. Okay. And for everybody else, we can say we can get directly to that node from A, but it's going to cost you an infinite amount of whatever unit you're using, right? Which is a good way of saying you can't get there. So once we've set that up, we go, and the way Dijkstra's works is we need to find out what this table is, how you get from A to any other item, and what the cost of that is, and how you get there. So first thing we do is we basically kind of expand out to see how far we're going, to see what the shortest cost is. So we resolve our two edges. We don't know, it doesn't matter which order we go in. So but what we check is, okay, we've got an edge between A and B. Does the cost of this edge plus the cost to get to the point we're starting at, which is A, so 0 plus 2, is that less than infinity? Yes, it is. So we are going to replace this with that edge cost, which is 2. Okay. Next, A to D. Does the cost to get to A, 0, plus the cost to use this edge, 3, is that less than infinity? Because infinity is what's already there. Yes. Okay. So we've resolved that. So A is done. Next, we go through and we go select the node that has the cheapest distance. If it's the node with the cheapest distance at this point, then it is solved because of the way Dijkstra runs his assumptions. No negative cycles. So B is solved next. Let's go ahead and go through its edges. B has an edge between, B to C has an edge, and B to E has an edge. B to C, okay, B to C is 5. Does the cost to get to B, which is 2, plus the cost to use that edge, which is 5, okay, simple math here, is that less than or equal to what we currently have for C, which is infinity? It's less than, so we update it. Getting to C costs a total of 7. This is the total cost. To get to C, it costs 7. And we get there by going through B. Okay. So the total cumulative cost to get to C is 7. We get there through B. Okay, next. We go and look for the next cheapest option. D. But we didn't resolve B to E. B to E, we do that same thing and we get B to E costs 5 because it's 2 plus 3. Okay, make sense? Next, we resolve the next cheapest one, which is D. D says, I've got one edge, which is D to C, which costs 1. So does the cost to get to C, which is 7, and so let's see, the cost to get to C right now through D is 3, which is the cost to get to D, plus the cost to use the edge to C. Is that less than or equal to 7? Yes, it is. So we're going to update 7 and say we can get to C with a cumulative cost of 4, and we go through D instead. Make sense? And now we just simply go through and keep doing this until all are done. We say, okay, what's the next cheapest? C is the next cheapest. C gets C to F is 2. The cost to get to C is 4. So for F, we would put down it is 2 plus 4, so it gets a total of 6. And C. Is everybody following this? Okay, next would be, and finally, we would check E off. E is the next cheapest one, 5. It costs 5 to get there. 5 plus 4, is that less than or equal to the total cost to get to F? 5 plus 4 is 9. The answer is no. So we do not update. So this one's actually good because it actually is constructed so that you have times where you need to update your previous answers and times where you don't have to update your previous answers. Okay, so this would be the final answer where we have our distances and our predecessors. Typically, the way I grade these is it has a set maximum number of points, like 8 or 10, and then I subtract 1 point for each entry you get wrong. Okay, and there's typically more entries than there are points.
So take your time with it and just work
Yeah,
out the
it's not, Dijkstra's is not hard. You can find 1.5 million videos on YouTube if my explanation sucked. But Dijkstra's will be on the algorithm. I plan on doing plenty more coding. Also, these reviews are typically at the end of one of the semester playlists that I have on the Canvas recording. So if you're interested, you can go to previous lectures and look at previous years and look at the lectures there.